Hello everyone and welcome back to CodeChef. In modern applications, databases are designed using relational principles, which means data is split across multiple tables to avoid redundancy and ensure consistency. Each table represents one entity, and relationships between entities are handled using keys. To retrieve meaningful information, SQL provides a powerful concept called joins, which allows us to logically merge tables at query time without physically combining them. In this video, we will go deep into the theory behind joins, how SQL engines interpret joins, and types of joins with real-world reasoning. So let's get started. Relationship types in ER model. A relationship shows how two or more entities are connected. First, one-to-one relationship, which is denoted using the sign 1:1. In a one-to-one relationship, one entity is associated with at most one entity of another type. Let's understand this with the help of an example. Person, passport. Now if you see, one person can have only one passport and one passport belongs to only one person. So both the entities, person and passport, are connected using one-to-one relationship. One person can have only one passport and one passport can be owned by one person only. And here you can see how to represent this one-to-one relationship between person and passport. Next is one-to-many relationship, which is denoted by 1:n. In a one-to-many relationship, one entity is related to multiple entities of another type. Let's understand this with an example. Department and employee. So one department can have many employees, but each employee belongs to only one department. So one to many. What is one here? Department. There is only one department. And what is many? Employee. So one department can have many employees, but we cannot do vice versa. That means one employee cannot have multiple departments. And this is how we represent one-to-many relationship in case of the example of department and employee. This is the most common relationship that is used in databases. Third is many-to-many relationship. We can denote it using m:n. In a many-to-many relationship, many entities from one side relate to many entities on the other side. For example, student and course. So a student can enroll in multiple courses and a course can have multiple students. So both of them can have multiple relationships with the other entity. Here we can see representation of many-to-many relationship in case of student and course. This type of relationship cannot be directly implemented in tables and requires a separate table because we need to store the data for each relationship which is there between any two different entities. Attribute types. Attributes describe the properties of an entity. So here we are going to discuss what are different types of attributes. First, multi-valued attributes. A multi-valued attribute can store more than one value for a single entity. Examples: phone numbers, email IDs, skills. So one student can have more than one phone number, one student can have more than one email ID, and same is the case with skills. A student can have multiple skills. Now how to represent ER diagram for such attributes that have multiple values? We show them using double oval. Second is derived attribute. A derived attribute is an attribute whose value is calculated from another attribute. For example, age. So if we have date of birth of a student, we can derive his or her age from that date. Second example is total salary, which can be derived from basic salary, basic pay plus allowances that are added or subtracted from that base salary. To represent derived attributes, we use dashed oval. Generally, derived attributes are not stored in tables to avoid redundancy. Redundancy means duplication of data. Functional dependency. Functional dependency explains how attributes depend on each other. Let's understand this with the help of a formal definition. An attribute B is functionally dependent on attribute A if each value of A uniquely determines the value of B. This means if A can uniquely determine all the values for attribute B, then B is functionally dependent on A. Looking at the notation for this kind of dependency, we can write A, then arrow B. That means B is functionally dependent on A, or A is actually determining the value of B. Let's understand this with the help of an example. Student ID, then functional dependency student name. This means for a given student ID, there is only one student name, and that student name can be determined using the given student ID. So student name is functionally dependent on student ID. It is very important to understand the concept of functional dependency because it is one of the core concepts in normalization. Next is partial dependency. Partial dependency occurs when a table has a composite primary key. Composite primary key means a primary key that is composed using multiple attributes. That means a single attribute is not a primary key but a combination of two or more attributes form the primary key. Second condition is a non-key attribute depends on only part of that key and not the complete primary key. For example, let's suppose we have a table named enrollment. Now enrollment has 4 attributes. First is student ID, second course ID, third student name, and fourth course name. Now the primary key for table enrollment is a composite primary key because it is composed of 2 attributes, student ID, course ID. Now what dependencies exist here? So student ID can be used to determine student name and course ID can be used to determine course name. Now here student name depends only on student ID and course name depends only on course ID. But if you see, the primary key is a combination of both student ID and course ID. So this is known as partial dependency. ER diagrams to tables, conversion rules. Now let us understand how can we convert ER diagrams into relational tables. Rule 1. Entity becomes table. So each entity becomes a table. For example, student, then in bracket, student ID, name, age. This means the entity is student. And what are the attributes of this entity? Student ID, name and age. Using these attributes, we can make a table for the entity student. Rule 2. One-to-one relationship. Add the primary key of one entity as a foreign key in the other entity. If you are not well versed with the concept of different kind of keys, please go to the playlist and check my previous videos in which I have explained different kinds of keys in database management. Rule 3. One-to-many relationship. Add the primary key of the one side as a foreign key in the many side. So in one-to-many relationship, one entity can have relationship with many other entities. So the primary key of that entity, which is 1, is added as a foreign key of the entity with which it has multiple relationships. For example, department and employee. So we know in one department there can be multiple employees. So between department and employee there is one-to-many relationship. Now for the entity department there are 2 attributes, department ID and department name. So let's suppose department ID is the primary key of table department, and an employee entity there are 3 attributes in the table, employee ID, name and department ID. So the department ID is same which was there in table department. Since department ID is the primary key for table department, it will be set as a foreign key in table employee. Next is many-to-many relationship. In this case, when we want to convert an ER diagram into a table, we create a new table with primary keys of both entities. For example, the relationship between entities student and entity course. So it is many-to-many relationship. It means one student can be enrolled in multiple courses and a course can have multiple students. So both the entities will use attribute student ID and course ID. So the primary key for such table will be a composite primary key which will have both student ID and course ID. Last but not the least, multi-valued attribute. So when one attribute can have multiple values, we create a separate table for such attributes. For example, student and phone. So one student can have multiple phone numbers, and when we want to create a table for such relationship, we need to add student ID and phone number. That wraps up a deep dive into SQL joins and multiple tables. If you truly want to master SQL, understanding joins at this theoretical level is non-negotiable. They form the backbone of backend development, data analysis, system design, and technical interviews. Next time, we will build complex multi-table queries using joins. Until then, keep practicing these joins on the CodeChef platform. Thank you so much for watching.